Swayam Prabha. Digital India. Educated India.
So let's resume. So what we are going to do in this session is a very basic review of virtual memory, privilege levels and traps. These three features of a processor, taking the Spark V8 architecture as an example, to see how these features in a processor help the operating system provide isolation, hardware abstraction, and so on, right? So this is so we were discussing virtual memory, and we saw the basic idea of virtual memory is to introduce a layer of indirection. Okay, so with this, some of the requirements get satisfied. First, requirement of a process being able to see the entire address space as its own. The programmer not having to worry about the actual physical memory layout, the code being relocatable and so on, portable. And efficient utilization of main memory, because if a process has a large memory layout, but it's not using all of these areas at one point of time, then it allows demand paging. So pages can be brought into the memory as and when required, right? So this essentially, this introducing a layer of indirection solve this problem. So this, however, introduces two issues. One is that every time you want to access the memory, you will have to first translate, and for translation you will need to read a page table entry, and for reading the page table entry you will have to access the memory again. So won't that mean two memory accesses, right? And the second is that these page tables can occupy a large amount of space in memory. So let me ask if there are any questions so far about this, the basic idea of virtual memory, and any questions? Okay, so feel free to stop me and ask questions. Okay, and I would really welcome if, even if there are very basic questions, because I think some of you do not have a background in operating systems as per your survey results. So you use this opportunity to ask basic questions, and so let's so assuming that this first thing can be solved by keeping a cache of recently used page table entries in the MMU. The second problem can be solved by using multi-level page tables, kind of like a hierarchical system. Okay. So let's look at how these page tables are maintained in the Spark architecture. So Spark uses 3-level page tables. Okay. So this is how it goes. Okay. So suppose this is the virtual address, 32-bit virtual address. Okay. The least significant 12 bits are used as a page offset. That means the other higher bits are used for somehow obtaining a page table entry. Once you obtain a page table entry, you get the corresponding physical frame for this address, and then you use the same page offset. So for example, if the page offset is 3, that means it's the 3rd byte at the start of the page. Okay. So instead of using just one page table, this is how it goes. This is divided into multiple page tables. Okay. So suppose this is the page table of the first process. So let's say we're talking about process 1. Now, first of all, where is this table stored? Okay, that address has to be pointed to by something. Okay, so this is pointed to based on the context. So currently process 1 is running on this. So it's process 1 that's running, and process 1's table needs to be used for doing the translations, right? So there is some mechanism for pointing to the address of the page table for process 1. So we'll see this and how contexts are maintained in a short while, but assume that we know this address, the start address. So the first 8 bits of the virtual address are used for indexing into this table. Okay. An entry in this table is not a page table entry necessarily, but it could be the address of a lower or next level page table. So it could be the start address of a page table itself. Okay. So such an entry is called a page table descriptor. So it's not a page table entry. A page table entry means basically something that gives directly the physical frame number of a particular address, right? This is in fact the address of the next level page. So suppose this index is into location 10 here, then there will be a page table descriptor. Okay, so this second level table is indexed using the next 6 bits. Okay, which could in turn point to another page table descriptor and so on. So it's like a hierarchical table. And the last 6 bits can be used to index into the level 3 page table. So level 3 table always contains page table entry. Level 2 and level 1 table can contain a page table descriptor or a page table entry for a very large page. Okay. So for example, if you have the first 8 bits and 6 bits used for directly going to a page table entry, this will be in level 2 table, okay, directly going to the page table entry, then this all of the others will be like an offset for the page. So this is 18 bits. So that's a single large page of size 2 to the power 18. Okay, so that's 64 KB page. So you can have large page sizes, or you can have finer page sizes, each of size 4 KB, by using the level 3 page table entry. Now, okay, so what do we gain by making this hierarchy? Essentially, if every element in this table points to another table, and if every element in that table points to another table and so on, if you add up all the area accumulated by all of the tables, it will be in fact slightly more than the single page table, right? You still need all this area. So what do we gain by doing this? First of all, it allows us to take advantage of sparse memory layout. So for example, in process 1, let's say the first few page table descriptors are populated and the later ones are empty because the memory layout itself is sparse. Okay, and then each of these, say, let's say for example, this process has the text area and the stack area. So the page table descriptor in the lower ranges of the address is existing, and the one in the higher address range is existing, and the middle ones are not valid. They are invalid entries. So corresponding to just these two page table descriptors, there will need to be only 2 level 2 tables, and then maybe a few of these entries are valid and so on. So at a time, not all of the entries are valid because the address occupancy is sparsely populated. The second is this possibility of having large pages, very large pages, for which you can have a page table entry in a level 1 table. Okay, if it's a level 1 table, then you use this 8 bits to index into it, and the rest of it is directly a page offset. So if the page offset is of what, 24 bits, then you have a large page of size 2 to the power 24. So but that page would have to be contiguous in the physical memory. So it's a large page which is actually contiguous in the physical memory. Okay, so it's essentially it has to be either 2 to the power 12 or 2 to the power 18 or 2 to the power 24. Okay, so in this manner, using a smaller amount of memory, one can create this page table hierarchy. Okay, but the question is still that all this is in the main memory. Okay, so now the MMU needs to be slightly more complex. Okay, what does the MMU do? Suppose it gets this virtual address. Okay, now the MMU will look at the first 8 bits and it knows the start address of the page table for this currently running process. It will use these bits to index into that table and look at the corresponding entry and check the valid bit. In particular, there is a type bit. Okay, there's an entry type bit actually. So entry type, okay, it could either be a page table entry of a large page, or it could be a page table descriptor. That means it's the address of the next level page, or it could be invalid, which means this address is not mapped in the memory. If it is invalid, if it's not mapped in the memory, then that creates a page fault. Okay, creates a fault. The operating system is invoked and it will have to fetch that data from the disk and create a page table entry here. If it's a page table descriptor, then the MMU will use this address here, okay, to obtain the base address of the next table, maybe level 2, and use these bits, 6 bits, to index into that table. And again check that entry. So depending on the entry type, this could again either be a page table entry of a slightly larger page, or it could be a page table descriptor, that means the address of the next table, or it could be invalid, and so on. So in the level 3 table, definitely there will be a page table entry, or it may be invalid. That means the page is not mapped. So either you find a page table entry or invalid. In the last level table, you may not find a page table descriptor. Okay, so if there is a page table entry, then that means the page is there and then you translate the address. If it's not there, you generate a fault. So the MMU has to do this traversal possibly multiple times. But remember that the MMU itself maintains a small cache of recently accessed page table entries, page table descriptors, and so on. So they are maintained in the TLB. So next time a similar address needs to be translated, the entry can be looked up straight from the TLB. So here is a concrete example of what a page table descriptor and page table entry can look like. So page table descriptor, the last 2 bits for both denote the entry type. Okay, so this could be invalid. It could be a page table descriptor. It could be a page table entry. The last value is reserved. Okay, so now let's look at the other part. If the descriptor, this part is the address of the next level page, the base address, right? Now the page tables are kind of word aligned, so these they have to be appended by a certain number of zeros to get the physical address of the next table. A page table entry, on the other hand, okay, should allow you to directly translate a virtual address into a physical address. So let's look at a page table entry. It has the entry type field as usual. It has access permissions, okay, which could be like, is this page read only or write or execute and so on. R refers to a recently accessed page. So it is set to 1 where if this page was recently accessed, which could be used for implementing some kind of a replacement policy. If it was recently accessed, then do not replace it and so on. Okay. And M bit is a modified bit. If M was 1, that means this particular page has been modified, and so it needs to be written back to disk if it is to be evicted. Okay. So C indicates cacheable. Whether you want this page table entry to be cached or not. Okay, if it is not, then this page table entry should not be cached. So let's take a look at the entire block diagram of a MMU. Okay, so here is the virtual address, 32-bit virtual address coming in. The last 12 bits are the page offset, which are directly used as a page offset in the physical address as it is. The virtual page part, the page number part, is used to first search into the cache. So this is the cache of page table entries present in the MMU, the translation look-aside buffer. So you see if there is a match. Okay. Remember that context is also stored here. So we'll see what is a context. So every process that is running is given a unique ID. Okay. And so the MMU might be storing page table entries for different processes. Okay. So for example, there may be this page table entry for process 1, another for process 1, another for process 2, and so on. Okay. And the current process which is running, that process's ID or the context ID is present in a context register. So here the cache may be storing translations for some other processes like say process 1, process 2, process 3, and so on. But the current process may be process 3. In which case you will only check all of the entries for process 3 for a match. Okay. So current context is 3. That means currently process 3 is running. So it's some ID assigned to every process. You check if there is a match or not. If there is a match, then we find the page table entry and we use it. If there is no match in the cache, then the MMU needs to traverse the page tables in the main memory. Okay, so how does it do it? So basically, we have to get the address of the first page table, right? So suppose context register is 3. That means process 3 is running. How do we get the address of the page table for process 3? So for this, we use the context table pointer register, which points to the page table for the current. Basically, this is another table which stores the addresses of each process's table. Okay, so let me show a diagram. So context table pointer register, this is the address of a large important table maintained by the operating system called the context table. Okay, this is a table which stores the starting address of the first level 1 page table of all of the processes. For example, this may be the address of the level 1 page table of process P0, process P1, process P2, and so on. So basically, you look at the context table pointer to see the start address of this table, and you index into this table based on the current context. So current context is stored in the context register, which is 3. That means process 3 is running. So you look at the third entry in this. This would give us the address of the page tables corresponding to process 3. So this is the start address. So this is referred to as a page table descriptor or the root pointer. Now we use this to get the start address of the level 1 table and use the first 8 bits to index into that table. If this is a page table descriptor, this will point to a level 2 page. Then use these 6 bits to index into this page table, and so on. Okay, so this is essentially what an MMU would do. Okay, and this is one way that contexts can be maintained by the MMU. So MMU can keep a cached copy of page table entries of multiple contexts. Okay, So here is an example where there is some virtual address tag, some tag A belonging to process 0, and then there is a page table entry. Okay, some other tag B belonging to process 0, page table entry, and so on. C belonging to process 1, page table entry, and so on. So whenever the context changes, like whenever one process finishes its time slice and another process is started, you don't need to remove all of these entries. Although there are instructions to flush out this. So there is a flush instruction for the TLB and so on. Okay. Especially when, let's say in the beginning, when you want to create the page tables and modify these page table entries and so on. Okay. So are there any questions about this context? I hope that okay. I hope that this part is somewhat clear. Okay, no questions?
Which do all processes have their descriptors in the context table pointer?
Can you repeat the question? I didn't understand.
Does every process that is executing on the system have a corresponding entry in the context table pointer?
Yes. So when the OS creates a new process, it should create an entry in the context table pointer, basically. So when it creates a process, it assigns a context ID and it creates a entry in the context table. So every live process, every process which is eligible to be scheduled should have an entry in the context table.
Thank you. Yeah, that makes sense. Thank you.
So so this kind of gives us an idea about what happens on a context switch, at least from the MMU perspective, right? So when process 1 finishes its time slice and the operating system now wants to give a chance to process 2 to run, you would think that at least what the operating system would do is to go to the MMU and change the value in this context register, right? So earlier it was 1, now it is 2. So 2 will be then used for doing matching of the page table entries, and correspondingly, we will look at the page tables for process 2. So notice that without having to erase the contents here, we were able to do a context switch just by changing this register value. I mean, instead of having to, write back all these things here and bring in all the information about the page tables of process 2. So process 1's page tables we were referring so far. Now we switch to process 2. So we want to use process 2's page table entries for doing our address translation. So if some of these entries are already in the cache, then it makes things much faster, right? They are already in the cache and we don't have to erase anything or read anything back from the memory and so on. They are already there. So it makes context switching fast simply by writing into the context register. Okay, we can switch context. When would somebody write into the context table pointer register? This is a register which points to the starting address of the context table. Right? This may happen only a few times after you boot. So initially, you might have some multiple stages of multiple stage bootloader. Okay, at every stage, it might set up its own page tables, and that's when you move from one stage to the other, you change this. So basically, if you have a multi-stage boot, then in every stage you might create a different set of page tables and rewrite this. But once you've done that, once you start running the operating system and your usual context switching, then there's no occasion to change this. Okay. Now, there are two other interesting things here. there is a fault status register and a fault address register. Okay. So notice that, and there is also a control register and so on. This is to control the operation modes of the MMU. It could be different. You could also disable the MMU to start. For example, when you just start off, you could disable the MMU altogether, in which case you just have virtual address is equal to physical address directly. It may be useful in certain cases to start off. Okay. Now, when the MMU is enabled and when translation is happening, suppose the MMU is not able to find a page table entry, or the corresponding page table entry is invalid. It's not able to find an entry. That means the page is not mapped to memory. This should create a fault, right? So it kind of interrupts the processor, kind of creates an interrupt to the processor. But once interrupted, the processor needs to know what caused the interrupt and what to do about it. So that information is stored in the fault status register and fault address register. So fault status register stores the information. It has flag bits to store information about what kind of a fault it was. Was it like a illegal, let's say in the level 3 page table, there was a page table descriptor found by mistake, kind of or an illegal page table entry, or was it like a page table entry not found, like page fault? Okay, so various faults are possible and they are encoded in the fault status register. So when a fault occurs, the OS code is the fault handler, the trap handler for that is required to read this fault status register and fault address register to see at which address, which virtual address did this problem occur and so on. So, and then take the necessary action. So, okay. So essentially this is a block diagram of a reference MMU. This is sort of specific to the Spark, but it's very similar to the MMU design, a three level page table design in other processors. So let's move on to something very simple to understand, but very useful. We are going to talk about privilege levels. Now, it's intuitive that you want to have different privilege levels, right? You want kernel to have more privilege than, let's say, a user mode program. So kernel can write to any memory locations and do anything. And let's say execute instructions that change the program status register and so on. But a user program should not be able to do that. So the Spark V8 ISE supports two modes. The processor can either be in the user mode or it can be in the supervisor mode. So it has these two modes. Some other architectures can support multiple privilege levels. Like say if you have not just one bit encoding whether you are, so Spark has one bit in the PSR register called the S bit. This is the processor state register, kind of like a status register. There is a S bit. If the S bit is 1, it indicates that the processor is in the supervisor mode currently. If it is 0, it indicates it's in the user mode. Some processors might use multiple bits and that results in a finer granularity in the privilege levels. So for example, x86 supports multiple privilege levels. So we'll focus on the Spark level. So here is a processor state register. Okay, these are the flags: negative, 0, overflow, carry, and so on. These are set upon executing some arithmetic and logic instructions. This is the supervisor bit. So if it is 0, it means the processor is currently in user mode. If it is 1, it means the processor is currently in supervisor mode. This is the previous S bit before any trap occurred. So whenever a trap occurs, you want to somehow, so if they say this is some user program and some trap occurs, you want to jump and execute to some, you want to execute some operating system code, maybe a trap handler, and then once that is done, you want to resume back and continue the same mode, right? So if you were in the supervisor mode, trap happens, you enter the operating system, you are in the supervisor mode for sure. But when you come back, you want to be in the supervisor mode. On the other hand, if you started off in the user mode, when a trap occurs, you enter the supervisor mode, you finish, you want to come back to the user mode. So somehow you want to remember what was the last mode, sort of a 1-bit storage. So this 1-bit stores the previous S bit before a trap occurred. Okay. ET is for enabling traps. So we will see traps in the next section. Let's just focus on the supervisor mode. So what can you do with these two modes? Okay, if you look at the instruction set architecture of all the instructions that are supported by this processor, some instructions are privileged and some instructions are non-privileged. So if the processor is in the supervisor mode, that means if S bit is 1, then the processor can execute any instruction, including privileged instructions. So all instructions are okay, can access any memory location and so on. On the other hand, if it's in the user mode, that means S bit is 0, then it can only execute non-privileged instructions, and attempts to execute a privileged instruction will cause a trap. Okay. So for example, in the user mode, if the code, there is a code that tries to set the processor status register, then that's a privileged instruction, and this is not allowed for user mode code. Okay. So this answers the obvious question that, if there is a processor state register, PSR, right? There may be an instruction like set PSR and some value to write into PSR register. If such an instruction is there, and if I am the user program, if S equal to 0, it's a user mode program, why don't I just execute this instruction and make S equal to 1? So now I'm the supervisor mode and I can do whatever I want. So it should not be allowed, right? So it should not be allowed for a user program to enter the supervisor mode. But if you are in the supervisor mode, it should be possible to enter the user mode, right? This seems okay. This seems possible. So let's see what other privileged things are there that only the supervisor mode can do. First is the instructions that access or modify the processor state register. This is a privileged action, and only in the supervisor mode can you modify the program state register. Okay. See, for example, enable traps. You want to enable the traps or disable the traps. This is a bit in the PSR register, so only the supervisor mode can do this. Second is the instructions to access or modify the MMU control registers like context pointer register, the current context, and so on. This only the supervisor mode can do. There are some privileged load store instructions to alternate address spaces. Okay. So we will see address space later if time permits, which is a feature in the Spark architecture. This is one way for extending the address space by sending out an address space identifier in parallel with the address. This is an 8-bit value, and it is a fixed number that indicates whether it's a user mode access or a supervisor mode access, and whether it's a read or a write, whether it's a read or a write. Sorry, whether I meant whether this is the instruction or load store instruction or data and instruction or data. Okay, so there are constants values assigned for all these combinations, 4 combinations, but there can be other values assigned. It's an 8-bit value, so other values can be used, and these together are used to address physical memory. So these address space identifiers can be used to assign a different set of chunk of addresses for devices and so on. So that's the thing in Spark. So only in supervisor mode can you specify some other values of address space identifiers. The last is there may be some special registers that are only accessible under the supervisor code. Okay, so there are such examples in the Spark architecture. This may or may not be there. So what happens is, let's say on reset, when you start execution, okay, by default S is equal to 1. So you start in the supervisor mode. Traps are disabled and PC is 0 typically, right? So you start from the instruction located at physical memory address 0. Also, typically the MMU is also disabled. And you assume that this corresponds to physical memory location 0000, which may be in some EEPROM chip, which contains like a fixed, firmware which you cannot modify. You cannot change that code. So it's like, okay, so that then leads to the bootloader and to the kernel and so on. So far, supervisor is still 1. So you have started off in the supervisor mode and you pass the control to the kernel, the operating system, is still in the supervisor mode. Okay. In this mode, the kernel can do anything. The program can do anything. Can access all the instructions, set up the MMU, okay, configure things and so on. Now, to perform privileged actions, okay, if once everything is set up, the kernel can then make S equal to 0 and pass control to the user program, right? By setting the context, by changing the context pointer register, it can jump to the next process. When this is done, when you are in the user mode cannot execute the privileged instructions. So if the user mode cannot execute privileged instructions, but it wants to invoke something that can only be done in the supervisor mode, then what is the mechanism for that? Okay, so you can go from supervisor mode to the user mode, but you cannot go from user mode to the supervisor mode directly. So how do you call kernel routines, for example, which have to be executed with a higher privilege level? You must use a trap. Okay, so what happens on a trap is that the control is given up by the user program and control goes to the code in the supervisor mode, to some other code. So you can ask for services using system call. So what is a system call is essentially implemented using a trap. Okay, and then it takes the control to the code which is already present and allows it to run the supervisor mode. So suppose this is the user code and here a trap occurs. Suppose this is user mode S equal to 0. Control goes to the a trap table, okay, which takes it to the kernel code basically, which is supervisor mode code. When this service has been performed, okay, then this returns back to the user code. It may or may not return back to the user code. I mean, it's up to what is the instruction here. If this is a return instruction, then you can return back to the instruction right after the one that caused the trap. Okay, so this is one way in which, although the user program cannot enter the supervisor mode itself and do something, it can invoke the kernel code, get some service performed, and return back the execution to itself. Example of such a service is like the write system call, a write to standard out. Okay, so this is a system call to write some characters to the standard out, which is essentially what is used by printf. What it does is basically whatever needs to be written, let's say a character needs to be written, puts it in a register or on the stack, and then it causes a trap. And the trap handler reads the value, prints it to the screen, accesses the device, and so on, and then jumps back. So the point of this is that you can enter the user mode from supervisor mode, but you cannot go from user mode to supervisor mode without using a trap. So one way to do it is to use a trap. Okay. So when a trap occurs, the operating system gains control, switches to the supervisor mode, performs some service, and then switches back to the user mode. So here is an example where your user process can use library functions like printf. Remember that this printf function is present in the stdio library when you say #include stdio.h. The library is still code which is in user mode, right? But it uses the right system call, which causes a trap and switches the control from here to the kernel code, where in the kernel it goes to the trap handler, which invokes code in the file system or the device driver and so on, gets the thing done, and then control returns back to the calling process. So that brings us to the discussion on traps. So before that, are there any questions on this privilege level? I think it may be, many of you may be already aware of this processor mode and supervisor mode, but it's good to have a recap. Okay, no questions. So let's discuss traps now. Like we already discussed, it's something like an interrupt. Okay, it's actually a vectored control flow. Okay, so basically you're executing instructions one after the other. A branch is where you know where to jump, and it only occurs in a specific place. So there has to be a branch instruction here. Okay, so if you have these instructions, there is a branch instruction. You know that there may or may not be a branch here. Okay. A trap can happen in any instruction. So like say this may be a load or a store instruction, but something goes wrong and this causes a trap. Or when this instruction is executing on the processor pin and interrupt on the interrupt pin of the processor, some pulse occurs, this interrupts the processor. Okay, there can be a number of such traps. So trap is something that unexpectedly causes the control to go from this point to some other point. Whereas a branch it's predictable. There is a branch instruction, so the control flow can only change in a branch instruction, right? Traps can occur any place, at any place. Okay. So what are the types of traps? They can be hardware traps and software traps. So hardware traps can be like an external interrupt arriving on a pin. It could be some exceptional condition that is caused during the execution of instruction. Okay, for example, there is a divide instruction and the dividend is 0, or the privilege instruction in user mode. User mode tries to access a privilege instruction, or so on. Okay. It could be an example of hardware trap is reset trap. Like when power switch is on, by default there's a reset trap which takes the processor to a certain location to be. So basically, it essentially takes the processor to PC equal to 0 when this happens. We'll see how. Some other traps are MMU page fault and so on. The other type are software traps. So the user can insert an instruction, a trap instruction. So it is in that sense, it is similar to a branch instruction, because in the branch instruction, you know that there is going to be a branch here. Similarly, if you explicitly have a trap instruction, then you know that there is going to be a trap here. Okay, so in that sense, it is not occurring anywhere. Okay, there is a trap instruction. So why would a programmer want to use a trap instruction? So it is causing sudden change of control and taking the control elsewhere to the operating system. It's different from a branch, because if you have a branch, you are jumping to some symbol which is in the same process. You're just jumping to some other location in the same process, right? A trap instruction, on the other hand, takes the control to the trap table, and from there on, it enters the processor enters the supervisor mode, and then you can do other things like change context and so on. So basically you enter the it takes the control to the operating system and can do other things with it. So this is one way using which we can implement system calls. Okay, some way by which programmatically you can cause a sudden change and cause the control to go to the operating system and put the system in a supervisor mode. Okay, and somehow eventually also return back. So this is a very useful feature. So a trap is a vector transfer of control to the supervisor through a trap table. Okay, so trap table is a table in memory that kind of indicates where is the code that is supposed to handle that trap. So in the usual set of processor registers, we also have a trap-based register, which we have not seen yet so far. Okay. What this does is this trap-based register points to the base address of the trap table. So there is a trap table in memory which has instructions about what to do when a trap occurs. Okay. And this contains the base address of the table, the starting address of this table in memory. Okay. The other field is the trap type field. Okay. So basically, let's say if it's an 8-bit field, indicates what type of trap just occurred. So there may be encoding like 000 indicates this is a reset trap, 1 indicates some other trap, and so on. So of all the 256 values, some are reserved for hardware traps, some are reserved for software traps. So every unique type of trap has a unique identifier here, which is used to index into the table. Okay. So suppose a divide by 0 trap has occurred, and suppose the trap type of that is 0x8. So what would be done is this trap base address, which points to the base of this, and this is used with the trap type as an index, and you go to the corresponding entry in the trap table. Okay. What does this contain? This contains basically 4 instructions. That's it. Just 4 instructions, any 4 instructions that you would want to execute when this trap occurs. Okay. So what do you put in the trap table? Okay, and how do you jump to the trap handler? We'll see that. So there is an enable traps bit, by the way. So when you power on, it is 0, and then when you do all the initializations, then you can say enable trap. So from henceforth, any traps that happen can be handled. So what happens is initially enable trap is equal to 0. You do some initializations, you initialize the MMU, this, that, you initialize the trap tables, you initialize the trap base address trap, and then you make enable trap equal to 1. So from this point onwards, if a trap occurs, then this trap table exists in memory and you can go to the correct trap handler. So here's our trap table. Okay, this can be used whenever a trap occurs. This is used to index into the trap table. It just contains 4 instructions, 32-bit instructions, which are executed. Okay. So when a trap occurs, and if enable trap was 1, traps were enabled and a trap occurred, first thing done. So this is what is done by hardware. This is hard coded in the processor. This is like the trap handling logic in the processor. what it does is first the traps are disabled. Okay. Then the current mode, when you are starting running this user program, if you were in user mode, when the trap occurred, you want to do something, the trap handler, you want to go back and continue in the user mode, right? If you are in supervisor mode, you want to continue in the supervisor mode. So you have to save the S bit somewhere. So you save the S bit in another bit called PS, the previous S bit. Okay, you set PS to S. You change the user supervisor mode. Okay, make it supervisor mode. So this may be user mode, you make it supervisor. And also you may want to eventually return. So you have to save the value of the program counter at this point of time. Okay, so program counters are saved in register 17 and 18 by convention. Then, depending on the type of the trap that happened, the trap type field is written. So essentially in the trap base register, this field is written into. And then control is transferred to the trap table. So PC takes the value of the trap base register, and the next PC takes the value of the trap base register plus 4. So what happens when you jump to this? So trap table essentially just contains 4 instructions, right? What can you do with 4 instructions? Well, you can't do much, but you can do a lot, right? If the instruction is a jump instruction from here or a call instruction, so you do something, then you jump to somewhere, which could be a largest piece of code, which could be a trap handler, and then you jump back here, okay? And this could be an instruction to return back, right? Or the instruction to return back could be in the trap handler here. So there is a special instruction to return from trap. It's called RETT, return from trap. What it does is it restores the saved value of supervisor. It restores PC from whatever was saved, R17. So remember, we had saved the values of S bit, PC, and PC, etc. It returns, restores them, and then passes the control back to this PC. So basically, one way to implement a time slice, right? You remember that there is a time slicing happening. So process 1 is running currently. Okay, the CPU is executing instructions from user process 1. So process 1 is in control. Now, how is the control transferred to the operating system, which will then pass the control to process 2 and so on? How is that done? So essentially, you cause an external interrupt, right? You may have a timer chip, you may have a timer device, which is set to interrupt the processor every few seconds, or every few milliseconds. So this would actually cause an interrupt on the processor, which is a hardware trap. Whenever that interrupt happens, so whenever this process is executing, enable traps is set to 1, so that traps can be enabled. This process cannot disable this, it cannot change the PSR register because it's a user mode. Now when it is running, if the timer interrupts, then it causes a trap and control goes to the operating system. So now the operating system may decide, okay, what is the trap, what is the kind of trap and so on. If it finds out that it's a timer interrupt, and that's because this process one's time slice ran out, then the operating system says, okay, now I can give control to process 2. So it will change the context register in the MMU and so on and pass the control to process 2. Similarly, process and also reset the timer. So process 2 will run, and after a while the timer will interrupt again and so on. So in this way, using traps, the context register, and so on, we can have simple multitasking. So in principle, we understand how multitasking could work using traps, virtual memory, and the context registers in the MMU. Now, there is one piece missing, one link missing in the understanding. Okay. there is one missing link in our understanding. If you recall, let me write here. If you recall, let's say this is process 1. This is process 1's memory layout and the address space, all the way from 002 to 2 to the power 32. All of these addresses belong to process 1. Similarly, here are the addresses that belong to process 2, and so on. Here, similarly, is the memory layout of the kernel part of the operating system. So how do you pass control from the program to the kernel, right? Well, that is a trap, right? A system call. But to actually jump to some memory location, it should be visible in the this process's memory layout, right? It should be visible in the process's address space. It should be visible to the processor. The process should know that this particular address exists. There should be a page table entry for that, right? So how is that done? So this is a missing idea. The idea is that, at least in Linux, okay, a part of the user's address space is reserved for kernel. That part is the same irrespective of what process it is. Okay, it's a fixed set of memory locations. For example, in Spark, the addresses from C00000 to all F is reserved for the kernel, okay, and it's mapped to the kernel. And the kernel, this part of the kernel is not swapped out of the physical memory. It's always there in physical memory, okay? It's not swapped out. And every process sees this as part of its address space, okay? What does this contain? This contains the trap tables. This thing contains the trap tables, page tables, and so on. Okay, essential parts in the kernel that every process needs to see. But process, although it can see this, it cannot directly go and mess with this, because this chunk it has maybe a read-only permission. So the process has a page table entry for this, but the permissions are read-only. It cannot go and mess with this. So it's kind of it can see this, it has access to this, but it cannot modify. And since all of the processes can see the same kernel address space, this is visible to them, it's easy for the code running in process 0 now wants to jump to the trap table. Suppose there is a trap and now it wants to jump to trap table, and trap table is located at address C0001000, suppose. Well, this address is visible in the process space, so it can jump to that address, which will be some trap table in this kernel space. So kernel code will be running, and then it might pass the control to process 2 by changing the context pointer. But kernel is still there at the same location. The trap table is still at the same location. Okay, that doesn't change. So this is one last link you may need to understand, to appreciate how a user program can always see kernel routines and can always jump to these kernel routines. Okay. So we are, let me summarize and then let me take questions about this. So our goal was to understand 3 architectural features that support program execution. So essentially very basic idea. Okay. First is virtual memory and the MMU. Second is the privilege levels. The third is traps. So with these 3 mechanisms in place, we have some idea of how an operating system, which is also a simple program, albeit running with S equal to 1 supervisor mode, okay, can provide for user processes all these features of isolation, multitasking, and so on, right? So operating system is simply another program which runs in the beginning and therefore runs in the supervisor mode. And using all these features provided by the MMU, by the privilege levels, and by traps, it can ensure isolation, protection, okay, for processes, and can create processes and so on. So I hope that at the end of this session, the links between the programmer's view, the architectural level view, and the operating system level view are somewhat clearer. So we have sort of finished the discussion of the session a bit early, and last 1 hour can be given for exercises which are there in this, which I have shared with you earlier about GCC and GDB.